In this video, we're going to define what a homogeneous system of equations is, determine the types of solutions you get with homogeneous equations, and then define and find the null space of a matrix. Now, just as a friendly reminder, we are currently working with systems of equations, but we're really starting to lay the foundations to work with matrices and with vectors, where a matrix is not necessarily a system of equations, it's just an array of numbers or equations themselves. So what a homogeneous system is, this will be starting to lay those foundations, is that we do L of S, remember then we're talking about a system of linear equations, A and B, where A is the coefficient matrix and B is the constants. With a system of homogeneous equations, the constants are all zero. So everything on the other side of the equal sign is a zero. So as an example, if we take a look at this, this is a homogeneous system because all of the constants, everything on the right side of the equal sign, are zero. Now, the theorem that we get for homogeneous systems is that they are going to be consistent, and we're going to have two possible outcomes for the solution. And we'll talk about those in a minute. But if you see a homogeneous system of equations, it is consistent. So you see that and you're like, woo, I'm going to get an answer. Okay. So if we set every single variable to zero, it will always be a solution of the homogeneous system. And what we call that is the trivial solution. So suppose that all of your variable values, x sub 1 all the way to x sub n, is equal to 0. In other words, my solution vector, which is x, is equal to the 0 vector, which we defined in our previous video. And then we call that the trivial solution. So if we take a look at this example here, and we put it into reduced row echelon form, this system becomes this. Now, we see that x sub 3 is 0, x sub 2 is 0, and x sub 1 is 0. This is the trivial solution. And since my n, the number of unknowns, is equal to the number of pivots, then we know that we get one solution, and that solution just happens to be the trivial solution. This is one of the two solutions that you're going to get in a homogeneous system. One of them is the trivial solution. Now, if we take this example where we have, again, a homogeneous system, and now we have 4 variables, but only 3 equations, we end up with 2 pivots after we put it into reduced row echelon form. Since my n is 4, my r is 2, number of pivots is 2, 4 minus 2 is 2. That means we have 2 free variables and 2 basic variables. Again, as a reminder, the basic variables are the pivots, the columns that have the pivots, and then the free variables are the columns that do not have the pivots, but also aren't a column of zeros. So if we take a look at the solution, one of the ways in which we can write the solution is in this form. I'm telling you that it is a column vector with 4 rows, and then I'm telling you that x sub 1 is the x sub 1 is the basic variable, and x sub 2 is also a basic variable. The other way in which we can represent the solution is, again, with a column vector, so that we can see here's what x sub 1 represents, here's x sub 2, x sub 3, and x sub 4, and this time we're declaring that our free variables are x sub 3, x sub 4, and they belong to the complex numbers. Another way in which we can represent the solution is that we can put the variable that we have as the free variable x sub 3. And this -1 is represented by the fact that in my x sub 1 row, my x sub 3 has a coefficient of -1. So in the x sub 1 row, the coefficient on that is -1. Now in the x sub 2 row, right here, there is no x sub 3. The x sub 3 row is 1. The x sub 4 in that solution is 0. And then this represents the constants, and we know, of course, this is the 0 vector, so we can, on the next step, we don't even have to write that, because there is no constants other than 0. And then over here we have the x sub 1, or excuse me, x sub 4 in the x sub 1 row. It has a negative 1 as a coefficient for the x sub 3. It has a positive 1 for the coefficient on the x sub 4. 0 and 0, x sub 3 row in this representation of the solution. You don't see any x sub 4, that's how come that's 0. And then of course in the x sub 4 row, it is a coefficient of 1, and that's where that 1 comes from. Again, we can then represent it this way. And since that last column of the homogeneous system is 0, then what we can do is we can work with just the coefficient matrices, and we don't have to worry about putting in an augmented form. And that's going to start getting us setting up with what we're going to be really focusing in on, which is matrices and vectors, and not just simply linear systems. So, and that's true. The reason I'm allowed to do just the augmented matrix or just the coefficient matrix is because no matter what I do to 0, add, subtract, multiply, it's still going to be 0. So here's the next theorem. It says with homogeneous systems that if you have more variables than you have linear systems and it's homogeneous, you are guaranteed to have an infinite number of solutions. So if we take a look at what we had 2 homogeneous systems. The first example up here is we had the same number of, this one up here, we had the same number of variables as we had linear equations, and so we get here the trivial solution. In this case, in this example, I had 4 variables, but I only had 3 equations, and it's homogeneous, which means I am going to have an infinite number of solutions, and I can represent it in one of these 4 forms. This form, this form, this form, or this form. Now what we're mostly going to be doing is we're going to start moving toward this form, and sometimes we don't even use x sub 3, we'll use maybe s or t. All right, so that's what that's saying. We have possibly 2 types of solutions, the trivial and then the infinite number. Now when we talk about the null space of a matrix, it is, in the way that we represent it is as this cursive n of a. It is also, could be do NUL, you might see it as NUL of a, you might see it in that form as well. And that is a system of all vectors that are solutions to the homogeneous system. And what I mean by that is, if I go back to that last way I represented my solution, notice it was these vectors. If I put this vector into this first equation or the second equation or the third equation as substitutions for those variables, it will make it a true statement. And the same thing is this. However, if I decide to call this another one, if I put 1, 1, 1, and 0 into one of these equations, it fails. And in fact, it fails right at the second equation. It may work for the first equation, but it doesn't work for the second equation. So what the null space is, basically, it is the infinite number of solutions representation. So the first thing you want to do when you find the null space, to find the null space, is if it's a homogeneous system, row reduce that homogeneous system of just the coefficient matrix. Because again, we don't need to augment it because all of the constants are 0. Then you determine if there's any free or basic variables. And then you're going to write the basic variables in terms of the free variables, like we did in the previous example. If there are no basic variables, like our first example, then my null space is the 0 vector. This example, my null space would be negative 1, 0, 1, 0, or it'd be 1, 0, 0, 1, because those are the solutions in terms of the free variables. And then we just write them as column vectors, and that's it. That's it for now.